According to chaos theory, most systems in the real world should be unpredictable. But if chaos theory does make things unpredictable, does that mean that systems which contain chaotic dynamics behave as though they are random? And if not, when is randomness not a good approximation of chaos? In this episode, we're going to discuss where and how chaos theory is an improvement on randomness to explain real-world phenomena. Rather than focus just on how it makes things unpredictable, we will offer insights into how we can tip the scales by understanding the bounds of unpredictability due to chaos, and not give up hope of some limited kinds of predictability for complex systems. Chaotic phase space. Spooky. But what is the butterfly effect, and what does it mean for modeling and prediction in the real world? A good place to start is by looking at a classic set of equations designed to illustrate chaotic dynamics, which provide a simple yet powerful way to explore nonlinearities in a mathematical simulation. These are the Lorenz equations. By exploring these, we can learn valuable lessons about what is possible in terms of mathematical predictions about the future for chaotic and complex systems like financial markets. The Lorenz equations are useful because they are relatively easy to understand with only a small number of variables, so we can see exactly what is going on. These equations are very powerful for illustrating concepts from chaos theory. Since they were introduced by meteorologist Edward Lorenz in 1963, they have become a classic example of deterministic chaos. The Lorenz equations describe the behavior of a simplified model of atmospheric convection. We're not going to discuss exactly what these three variables represent. The key thing is that we can plot their evolution in time in a three-dimensional space, where each variable is represented on an axis. In chaos theory, this forms what is known as a phase space, where each point in this three-dimensional space corresponds to a specific combination of the values of x, y, and z at a given moment in time. The concept of phase space is fundamental in understanding the dynamics of a system. It is a mathematical space in which all possible states of a system are represented. The dimensionality of the phase space is determined by the number of independent variables. Since there are three variables, here the phase space is three-dimensional. So it's easy to visualize, because we can simply plot it against these three axes. Thus the motion or evolution of this system of equations can be visualized as a trajectory in this phase space. Commonly, these equations are plotted using what are called difference equations to numerically solve them. This allows us to iteratively update the values of x, y, and z in discrete time steps. This raises the tantalizing possibility that maybe, if we modified such a chaotic system, we could represent, and therefore predict, financial market behavior as well. Or at least, we can use this sort of simple chaotic system to train algorithms to better anticipate market movements. For example, if we plot just one variable against time, then we create a nice time series. Now we have something that begins to resemble the unpredictable up and down movement of the stock market over time. Initially this looks promising, but there's a catch, and this is where the butterfly effect comes in. Sensitivity to initial conditions. The Lorenz equations are known for demonstrating the butterfly effect. We can demonstrate this in our phase space here. We start with two dots, one blue, one red, close together, but in slightly different starting positions. Each dot will follow the Lorenz equations as we iterate each step of the model. In the very beginning, the two dots stay close together. But eventually, a gap opens up between them. For a while, it almost looks like one is following the other. But at some point, the paths they will take start to diverge quite dramatically. You can think about this as representing the size of an error in an estimate of the starting values, growing over time. If the blue dot is the real world, then think of the red dot as representing some estimate of the starting value, which is slightly wrong. Eventually, the paths each dot takes become so different that they appear to have no relation to each other at all. Thus, the butterfly effect comes out of the Loren equations due to their sensitivity to initial conditions. The butterfly effect is a common and popular metaphor. In the words of Lorenz, the flap of a butterfly's wings in Brazil could in theory set off a chain of events that ultimately leads to a tornado in Texas, because even small changes to the atmospheric conditions can lead to significant changes in the way the whole system evolves down the line. But does this make prediction completely hopeless? Not at all. In fact, there are tantalizing hints of predictability in this. For one thing, if this system behaved randomly, we would expect that the value of the system in one time step would be independent of the value in the next. But looking at the evolution of our simple chaotic system, this clearly isn't the case. We can see that the system is, at least in the short term, somewhat predictable, with momentum swings that go one way and then the other. So effectively, it's the long term that is unpredictable. But there's another interesting property of chaotic systems, and that is that they generate so-called strange attractors. These attractors become more obvious after running our simulation for a large number of steps, and tend to a consistent geometrical shape. Hence the simulation is attracted to these shapes. The term strange reflects the non-intuitive and complex behavior exhibited by these attractors. Generally speaking, the structure of these attractors is not simple or regular, and may include folds, curves, and self-replicating patterns. A curious thing about the trajectories in the phase space of a chaotic system is that they are non-repeating. There's a very important reason for this. That is, if it did repeat, then it would in fact be a periodic system, and therefore predictable. The non-repeating nature contributes to the strangeness of the attractor. This is also weird because it implies that the trajectory in the phase space is infinitely long, yet is constrained in a finite space. We can see this if we allow the simulation to continue to run for a much longer time. The space begins to fill up and look like it is completely full. But as we zoom in, we see that there are actually gaps between each loop and the strange attractor. The further we zoom in, the more structure we see, and eventually it becomes clear that there are gaps between the paths. This characteristic that as we zoom in more and more, we see more and more structure, is a property of fractals, so this attractor is starting to show fractal-like qualities. Generally speaking, chaotic attractors display strange and often self-similar behavior, where patterns at different scales resemble one another. This trait adds to their strange quality. This is all very promising for a chaotic model of stock market behavior, but if we compare this to how the actual stock market looks, we see immediately that there are big differences. Stock market time series are much spikier, and also exhibit dramatic movements in compressed time frames. We can't explain or simulate these with a simple chaotic system like the Loren Equations. The reason for this is that the Lorenz model is far too simple compared to the complexity of real financial markets. Data from financial markets and many other complex systems are much better characterized by fractals. So simple chaotic systems have structure, but it's not enough of the right kind of structure to describe financial markets. In the next episode, we are going to further explore why randomness, like random walks, is not a good approximation of the stock market, and also look at what is the right kind of structure to describe stock markets.